Good afternoon, everyone. I'm going to talk about hotspots analysis when you get data. I believe many of you have your own data, then how you analyze them. Specifically, I'm going to focus on one method first. Anyway, and then I will talk about the factors affecting results, and then we'll focus on another method. The get is G. So I'm just trying to play with it, and I will show you some interesting results, initial results. Don't worry about the data I'm working with, mainly soil geochemistry. If you work on your biochar or whatever data, I believe when you get data, you really want to analyze them. So in Ireland, we do get a lot of data, and then we can focus on heavy metals. That's what I've been working with. Specifically for heavy metals, they are affected by quite a lot of factors, natural and human. That definitely causes very complicated spatial distribution. Therefore, there's a challenge. How do we find out the hidden information, hidden patterns? One idea is to perform hotspots analysis. And more importantly, if they are significant. First, I'm going to explain the method local Murasai, and then we'll talk a little bit more about the G. That's one I'm just playing with it now. I'm going to use the data of lead concentration in Galway City as an example, where you can think about your own data anyway. Don't have to be lead in Galway, okay? Perhaps in your city or different elements. Now, this is the study area in Galway, in Ireland. It's, in fact, Galway is the European Capital of Culture, 2020. Now, that's a very clean area and very little pollution. It's interesting to find some information there by sampling it, specifically for lead. You will see that lead is concentrated in this urban area, and you get lower concentration in the suburban area. Now, we want to really know if there are any hotspots. So this is the method we use. What can we do use that? Specifically, we can find high-value clusters, that's number A, and also low-value clusters, that's number D. And also we can find high-value outliers, number B, and then low-value outliers, and number C. And number 5 is not significant. So using this one, we are able to identify those features if you get your own data. Well, anyway, that's how we identify it. And in fact, I want to show you the results are affected by quite a few parameters if you use that one. First one is the distance band. Specifically, how we define the weighting function. There's Wij. That's the one we define the neighborhood. Specifically, we will choose a point. We want to know if it's a hotspot, where it's there's 4 situations I explained to you: high cluster, high value cluster, low value cluster, low value outlier, or high value outlier. How do we do that? In fact, we will define a distance band and then calculate this relationship with the neighbors. And then the distance band, we can choose that within that area where we use them for calculation of the parameter I, and then the others will give them weighting 0. Anyway, that's the one. We choose the band of 1,000 meters, then we get the results. Those are the hotspots clusters, high-value clusters, and then you get some low-value clusters, and also some outliers. So that's the results when we choose the distance band 100 meters, 1,000. And then if we choose to 2,000, and then we choose 5,000. So you can see the results are different. But keep that in mind, the patterns are fairly there. Urban area, you always get high values, high value clusters. So the results, even though the patterns are different, but they are, the values are different and the patterns are quite similar. Another factor is the data transformation. We use box Cox or normal score transformation. Then we use box score transformation, get that result, and then use normal score transformation. And that's no transformation. So you will see the results are also different. So the results are also affected by data transformation. And also, if we have some extreme values there, if we take them out, then we will see the different results there again. So anyway, just want to demonstrate to you, we use the methodology. The results may be slightly different. But the patterns are there. Urban area, you always see those high-value clusters. Of course, this method can be used in many case situations. For example, this one, we found the pollution in Galway. In fact, I used the hospital's analysis to find this sports ground that's contaminated. And in fact, that made me a celebrity in Galway because it's so clean there. And we can show this in 3D. And also, because in Ireland we don't have too much pollution, so one of the pollution sources is the bonfire. So we also analyze bonfire hotspots. You can see very clearly the hotspots are in line with the bonfire location. And also, you will see the hotspots are along the roads. This is the rare earth hotspots and cool spots in London. You'll find they are very much in line with rock type. Now this is very interesting. I want to talk a little bit with you. That's phosphorus in London. The data has been in BGS for a long time, and phosphorus is elevated along River Thames and also along River Lee. And here I found a breaking point. We don't have many hotspots there. If the theory of along the river and urban area goes on, we should have hotspots there. Unfortunately, we don't find them. In fact, we found that the breaking point is the highest tidal point. And the tide has mixed the phosphorus in soils, mainly in sediments. So that's the new discovery using hotspots analysis. Without that, you won't be able to find that result. Now, let's move to another one. There's a new idea now, big data. Data in geochemistry is getting more and more and bigger and providing more challenges. It has quite a few features, several V, volume, variety, velocity, and even more V. Okay, there are many talks about those V's. Anyway, we try to link that with geochemistry. Specifically, we have European data, that's agricultural data. And my colleague, Clemens Ryman, is very clever. He put all the data into the periodical table. Perhaps you have never seen that map. He's really clever. So that's really big data, okay. And in Ireland, we get a TEAS program. We're collecting geophysical data, use airplanes, and also very high density data of geochemistry. And currently, Northern Ireland, the border area data are available. So far, those data are downloadable. We get more than 10K samples there. And in fact, currently, they're covering Galway area. That's why I become interested in it now. And I think you have to acknowledge this is really big data. This is Alaska. And the number of samples is more than 170K. Okay, that's a real sampling. That's compiled by Geological Survey, US Geological Survey. And also, we are trying to produce the chemical Earth. Perhaps, have you ever heard of chemical Earth? It's led by UNESCO Center of Global Geochemistry Center. And we are trying to produce the chemical on the surface of the Earth. So anyway, big data is on this way. Now, what happens? So what? We get big data. In fact, I found that problem more than 10 years ago. When we get big data, at that time I didn't notice the concept of big data. Many of us don't know either. But we know sample size. In fact, at that time I called large sample size or whatever. I worked with the data from US Geological Survey. The original data more than 48K, and then when it declustered, anyway, I used declustered data, 16K anyway. for that data, we found a big problem. What problem? When we use data analysis, statistics, we always want to decide either parametric or non-parametric, right? First step is check their normality. Have you found that none of them could pass the normality test? None of them, all of them failed. Normally, we will get some of them pass. Unfortunately here, none of them pass. So I performed a transformation, still none of them can pass. So it's really strange. Well, as a geochemist, I didn't really know that. I talked to our professor in statistics in Galway. He told me the sample size is too large. Large sample size enhances the power of statistics tests, leading to rejection of almost all tests. What happens? Not only just test for normality, okay, if you want to do ANOVA, or even just whatever you want to do, and I want to tell you the results are definite rejection. Or you may see was affected by soil type, for example. Okay, I just randomly classify the data into different soil types. You will definitely get rejection. So keep that in mind when you get large data. First problem, statistical tests does not work. So I did try to see how large is too large. Well, generally, you can say when numbers reach 1,000, you have to be very careful anyway. So that's my suggestion there. Now, it does really lead us to have a new way of thinking. I think when you get large data, big data, you really think about the patterns instead of the statistical tests. So I'm just using another method called GETIS. This method helps us to identify high-value clusters and low-value clusters. Now, interesting results coming out now. Left, you can see very nice clusters. This map shows much clearer patterns than the original data. Even much clearer pattern than the distribution map. Okay. So we are working on it now, try to explain it. No, that's not so interesting. I want to tell you something even more interesting. Total organic carbon. I think many of us work on that. Have a look at that. You will see the patterns there. In northern part of Europe, you get high-value clusters. In southern and central Europe, you get low values. Okay, just keep that in mind. And then for pH value, you can see that definitely opposite, right? I believe everybody understands that. Now, I will show you something really interesting there. Have you found something interesting there? In Central Europe, Poland, both of them are cool spots. That's really interesting. Because they should be opposite to each other. Their relationship are opposite. Okay. So that's really interesting. So I talked to my colleagues in Europe. They told me Central Europe has they're very sandy. So luckily in the database I have silicon. So you can see indeed we get a very high value cluster of silicon. So just use the cluster analysis. We are able to identify those hidden information. Normally people have never found LXC. I've never seen anybody seeing that. Like here you will see the pattern so clear, automatically identified. Another story I want to show you is this one. Well, I'm working with my colleagues to try to write a nice paper anyway. And this one is calculated based on more than 170K samples of Alaska. You have never seen such a map, I would like to see, because I just produced it. Again, this one shows it's aluminum. Okay, there are the cool spots. Those are hot spots. I believe they show some very clear geological boundary there. So I'm working with colleagues from Alaska Geological Survey, so we're trying to link it. So when I get a good time, I will work on it in detail. So anyway, I've shown you the power of automatically identify those spatial clusters, or just hotspots analysis. So Just want to see the first method I use local bronze. I used it for many years. And there are some factors we need to keep in mind. And when we come to the area of big data, really think more about patterns instead of performing statistical tests. Just really keep that in mind. If you get a large number and perform statistical tests and try to interpret it, you really need to be very careful, because you always get the result of a rejection of null hypothesis. Thank you very much.
Thank you very much for this interesting
Yes.
coffee.
Okay, first of all, I think this was very interesting presentation. But do you think if you study patterns rather than applying stats, does this mean there are no outliers in the data?
You are right. We get a huge number of data where you can also identify outlier, of course. You can use conventional way, just ranking it, okay, and then you get higher one. Definitely there are there. But for this one, if you identify specific outliers, if you get a large number, what do you do with that? Even for a small number of samples, it's really virtually impossible for you to go back to identify them. But still useful, of course. For example, I think in China geological survey, they just use a threshold to identify outliers, and use that one to identify mining sites. In fact, during the past 30 or 40 years, they have identified more than 2,000 mining sites, just using that kind of, when not hotspots, and I suggested that to them to identify this one, use this one. There are two methods here. When we get a huge number, I become more interested in the patterns, because we are interested in seeing the big patterns and see what are the controlling factors at that level. So definitely outlier is also important. But if you get more than 100K samples, I tell you that, what do you do with that? Definitely, you can do it. Thank you.
Okay, thank you. One question.
I'm from biogeochemistry actually, and hotspots is one of the things we also deal with.
Thank you.
But it's not, the scale is very different actually. You are dealing with a regional level or a country global level kind of thing. We work only in the field levels. And we look for hotspots where the processes are active compared to the other spots where they are not active. Can we use this tool?
Any level.
Scale? Yeah.
I just want to tell you any level. In fact, when your data contain coordinates, in fact, I think just recently we published a paper, I think, chemosphere. What we did, it's not field, even smaller than field. It's the membrane. This size is DGT membrane. Have you ever heard? Well, I think you know DGT. We get the membrane and then we get scanned images of the data. Then we can see the hotspots there. So I just use this one's X coordinates as X, this one as Y coordinates. It's GIS. Don't worry, you can apply anywhere. So I mean, it's a field, of course. Definitely yes. Thank you.
Thank you. Is there one more question? Good. No one more question, please.
I have one question. You can is this slides or data is just a soil surface condition or include subsurface? Can you join the subsurface condition? Or do you have subsurface data about all of that?
Thank you. Yeah, so far we work on one layer. Yeah, so you can whatever layer you want to work with. So it's the same. The methodology is the same. But if you do have two layers, top layer and subsurface layer, then you can do them separately, and then you can do some kind of ratio there. In fact, I worked with my Chinese colleague. We found
Thank you very much.
Thank you.
Okay, thank you very much. Let's thank Dr. Zhang again for this
Thank you.
presentation.